Chlorpyrifos is the most widely used organophosphate compound and is used in agriculture as an insecticide for insects and worms. It was developed and patented by Dow Chemical in 1966, and its use has expanded ever since. Its potential effects on humans and wildlife has been the subject of research in the last few decades, leading to several national and statewide regulations. The compound forms a white crystal at room temperature. It does not have any hydrogen bonds to donate, which makes it difficult to dissolve in water and allows it to have high lipophilicity, or ability to dissolve in fats and lipids. It has a high mercaptan-like odor, which smells similar to rotting cabbages. The most common use of chlorpyrifos is as a pesticide in agriculture, where it is known commercially as Lorsban, Brodan, Dursban, and Doco 179. The chemical kills insects and borers on many crops, including corn, soybeans, fruit trees, strawberries, and even Christmas trees. It is estimated that 8 million pounds of the compound are sprayed in fields annually. In fields near residential areas, the EPA allows 2 pounds of active ingredient to be sprayed per acre. It was previously a widely used household insecticide before use in the home was banned in 2001. Humans can be exposed to chlorpyrifos by oral, dermal, and inhalation routes. Oral exposure can occur by ingesting food that was sprayed with the chemical, and dermal exposure can occur by any direct contact with skin. Inhalation is especially a concern near agricultural areas where chlorpyrifos is sprayed. However, a test of urban homes in North Carolina found chlorpyrifos in all of the indoor and outdoor dust samples, so this is clearly not just a contaminant in rural areas. The National Human Exposure Assessment Survey in Maryland sampled areas of the home and parts of the diet of 80 individuals. They estimated that the mean daily exposure to chlorpyrifos was 1,390 nanograms per day, and exposure from inhalation accounted for 84% of that daily exposure. Children are at a greater risk for chlorpyrifos exposure due to behavior and biology. Children frequently play outside when they come into contact with the soil, and they are breathing in air that is closer to the ground where pesticides may accumulate. Chlorpyrifos has a high lipid solubility, so it may also accumulate in breast milk and be ingested by infants. In addition to its inability to dissolve in water and its lipophilic nature, chlorpyrifos has another chemical property that leads to the severity of its toxicity: bioactivation. When chlorpyrifos enters the body, it is rapidly absorbed and metabolically activated by hydrolysis into a more toxic form, chlorpyrifos oxon, before metabolizing to become the metabolite TCP. Chlorpyrifos first undergoes oxidative desulfuration into chlorpyrifos oxon and then is hydrolyzed by A-esterase into the metabolite TCP. The toxic metabolite chlorpyrifos oxon can also be formed in the environment by reacting with oxidizing agents. The TCP metabolite does not occur in the environment naturally, but has become prevalent due to the use of chlorpyrifos, its parent compound. Chlorpyrifos is largely residing in fat, but TCP tends to stay in the liver and kidney. This compound has some toxic effects as well, which can be seen in the fish embryos that developed abnormalities with increased TCP exposure. TCP is often used to measure chlorpyrifos exposure since it is excreted in urine. TCP levels were measured by the CDC in their biomonitoring study, where they found that of nearly 500 pregnant women living near agricultural areas, 76% had detectable levels of TCP in their urine. Chlorpyrifos is designed to attack the nervous system of insects, so it is a serious concern if humans are exposed, since the chemical may attack our nervous systems in a similar way. Exposures to humans can lead to nausea, dizziness, and confusion, and researchers have shown some correlation with exposure in epilepsy, autism, ADHD, memory problems, tremors, lower cognitive ability, and nerve disorders. I will focus on its potential contribution to autism spectrum disorders. Autism spectrum disorder is a developmental disability that is characterized by deficiencies in social interactions and repetitive kinds of interests and behavior. A monitoring study published by the CDC in 2019 shows that prevalence of autism spectrum disorder increased slightly across the United States from 2010 to 2014, with about 17 out of 1,000 children affected on average. It is important to note that the cause of this disorder is at present unknown and is the subject of many research and public health studies. However, due to the rise in diagnosed cases among children, this disorder is a major health concern, and it is important to consider both potential genetic and environmental contributions. There has been significant research on chlorpyrifos' neurotoxicity, which we will go into more detail on later. The pesticide's action as a neurotoxin has raised concerns about its impacts on a susceptible population, children, especially during development, and how it may contribute to developmental or cognitive disorders throughout their lifetime. The Childhood Autism Risks from Genetics and Environment, or CHARGE study in 2014 examined the prevalence of autism spectrum disorder cases in homes that were 1.25 to 1.75 kilometers from agricultural sites that used chlorpyrifos during pregnancy. They analyzed it independently and as a group of pesticides, of which it was the most abundant. They focused on California, since it is the state with the highest agricultural production in the United States. The CHARGE study found that children with autism spectrum disorder were 60% more likely to have organophosphates applied near the home, especially during the second and third trimesters compared to the reference group. This was a correlational study, so it did not attribute autism spectrum disorder to the specific dose of chlorpyrifos. However, some research has been done on neurodevelopmental effects in zebrafish, rodents, and C. elegans at different doses of chlorpyrifos, and they began seeing some adverse effects at low doses of less than 1 milligram per kilogram per day. Next, we will explore how specifically chlorpyrifos acts as a neurotoxin. Normally, the neurotransmitter acetylcholine is released during depolarization of the neuronal cell and acts on neuromuscular and neuroglandular receptors to elicit a cellular response. The enzyme acetylcholinesterase is designed to break down the acetylcholine neurotransmitter in the synapse to terminate its actions. Chlorpyrifos is an acetylcholinesterase inhibitor, so it will prevent breakdown of the neurotransmitter. Here is a diagram of normal neurotransmission of acetylcholine, where there is a normal response from the transmitter binding receptors on the receiving cell, and acetylcholinesterase is working to terminate the signal by degradation. When we add chlorpyrifos, it prevents the degradation at nerve endings, which results in an excess of the neurotransmitter acetylcholine and continuous stimulation of the receiving cell. Some symptoms from overstimulation of acetylcholine receptors during acetylcholinesterase inhibition are twitching, paralysis, vomiting, and confusion, all of which have been associated with either low or high exposures to chlorpyrifos. To elicit paralysis, acetylcholine will build up on nicotinic acetylcholine receptors, which are found in the central and peripheral nervous system, as well as in skeletal muscle cells. Muscle fibers will twitch uncontrollably before leading to flaccid paralysis. So we know that chlorpyrifos acts as a neurotoxin by inhibiting the enzyme acetylcholinesterase, which can lead to several known health outcomes, and has been the basis of research on the compound's potential acute effects on the nervous system, especially during the developmental phase. One such research project was published this year by Cristian Perez Fernandez and colleagues, which aimed to understand medium and long-term effects on low doses of chlorpyrifos during the postnatal development stage in Wistar rats, with a focus on several biomarkers of autism spectrum disorder in humans, including sociability. They didn't establish a link between the disorder and chlorpyrifos exposure. However, I thought their dosage study presented some interesting effects regarding social behavior and exposure. This research group examined how low doses of chlorpyrifos during the postnatal period in rats could lead to social outcomes during adolescence and adulthood. They hypothesized that the dose of 1 milligram per kilogram per milliliter per day for 6 days would lead to decreased social activity in the rats. Of a group of adult and adolescent rats, they exposed half of each to chlorpyrifos. They also had an equal group of male and females. They administered diluted chlorpyrifos orally, and their control group was given corn oil. To analyze behavior, they used the Crawley test in an open field, which involved 5 minutes of free exploration, 10 minutes of visually seeing and smelling another rat, and then a social decision in the last 10 minutes. They sacrificed a random collection of these rats at the end to analyze molecular data as well. What they found was that the adult females had higher sociability and adult males had lower sociability when exposed to chlorpyrifos, all at doses without toxicity of acetylcholinesterase inhibition. Interestingly, there was no effect in adolescent rats. They found that their results on social behavior were limited and unable to create a link between chlorpyrifos exposure and autism spectrum disorder. However, there are some behavioral effects linked to a very low exposure, and they may have seen more differences had they increased the dose to an amount that actually inhibited acetylcholinesterase. I think this study was still important for toxicology because it examined exposure at relatively low levels and was concerned with how an environmental toxicant may play a role in a cognitive disorder that we don't really know the cause of yet. As a side note, they also conducted an experiment where they had the rats fight each other to see if exposure had an effect on dominance, but they sadly didn't find any statistically significant differences from that experiment. We've primarily focused on chlorpyrifos' chemical mechanisms and resulting health outcomes in humans. However, this compound is extremely detrimental and toxic to aquatic life. Aquatic species are at risk of exposure from contamination in rivers and other bodies of water if they are near areas where the chemical is sprayed, since the chemical can be mobilized by runoff from fields or orchards into groundwater. And from what we have discussed already, chlorpyrifos cannot dissolve in water very well, if at all. A study on the freshwater fish, Cyprinus carpio, found that the medium lethal contamination was 5.28 parts per million, which was the point where 50% of the fish died. This research also found that chlorpyrifos exposure at 5.28 parts per million led to extreme destruction of red blood cells due to the binding of the toxicant to hemoglobin and built up in erythrocytes. Despite studies that have shown chlorpyrifos has toxic effects on humans and wildlife, chlorpyrifos is still open for purchase on the market for agricultural use, where 8 to 11 million pounds are applied to fields annually. This is unfortunately due to legal battles throughout the last 2 decades and from the switch in administrations 4 years ago. We already discussed that chlorpyrifos was banned in 2001 as a household pesticide due to research published on its effects on development in children. Similar EPA research on chlorpyrifos' potential effects on children eventually led the Obama administration to announce in 2015 that chlorpyrifos use will be banned entirely, including for agricultural reasons. However, several recent developments from the Trump administration has, at least for now, ensured that chlorpyrifos will be available for purchase. In 2017, the EPA Administrator Scott Pruitt rolled back on the previous administration's decisions before any of the promised measures had taken place. This decision was rejected by a federal appeals court in 2018, but the new EPA Administrator, Andrew Wheeler, rejected this decision just last year. So, for now, chlorpyrifos remains a dangerous and toxic chemical in our environment, and certainly our bodies as well. Chlorpyrifos is not alone. The EPA has registered more than 34,000 pesticides, and only 5 parent chemicals have been banned by the Toxic Substance Control Act ever, and it was created in 1976. It is understandably difficult to reach a consensus when deciding on whether or not to enact governmental regulations on pesticides, since they have to weigh the benefits along with potential health effects, and there will be dedicated parties on either side of the argument. For example, in Michigan, chlorpyrifos is the main way to combat borers, which destroy cherry trees. Dr. Nikki Rothwell of Michigan State University once stated that based on chemical trials, chlorpyrifos is currently the only registered insecticide that provides reliable control of the borer complex, and without it, the Michigan cherry industry would suffer tremendous losses. Michigan provides 75% of the nation's cherries, so there will undoubtedly be passionate support for the inclusion of chlorpyrifos on the market for agricultural use. It is important to not forget about health outcomes in humans and aquatic life. Chlorpyrifos' actions as a neurotoxin, as well as its potential contributions to disease, leave populations of people, especially those living near agricultural areas where the pesticide is applied, as well as children, at risk. After learning about this compound and its toxicity, I'm certainly in favor of more governmental regulations that will eventually phase it out of use entirely. I encourage you to explore how chemicals in the environment affect our bodies and to examine how these chemicals may play a role in your life. We are made up of molecules and complex biological processes that are sensitive to even small disturbances, including chlorpyrifos.